Ready to go? Okay, cool. All right, thanks. So it's wonderful to be back in Bangalore after 6 years or so at this wonderful workshop. So today I'd like to describe, basically it's some sort of condensed summary, but also with some open problems of some work done over the last 4 years with all these different collaborators on all kinds of different papers. But the main question as written in the title is basically the following question. So here's our beloved ADS-CFT correspondence, where an exact CFT is equal to some exact quantum gravitational theory in ADS, or ADS times something. We usually think of this as string theory, but then UV and non-perturbatively completed and so on. And we don't know how to compute anything here, except by computing something here. So what we very often do is when we want to do any computation here, we make a semi-classical approximation. We replace the string theory or the quantum gravity theory by some effective gravitational theory, and we very often just do semi-classical computations in ADS-CFT. So that's an approximation. That approximation essentially boils down to finding the classical solutions of the field equations, the so-called saddles of the theory, and then we compute perturbative corrections in those saddles. That's an approximation, and the question that you may want to ask is, what is the corresponding approximation you have to do to the exact CFT to find an equality below? So what exactly is this approximation rephrased in CFT language? You might think that somehow this is nothing but a boring low energy approximation to the CFT, but things are a bit more interesting because this is, although this is some sort of low energy approximation, it's a bit more interesting than your usual low energy approximation, because this low energy approximation contains, for example, black holes. Black holes know about the high energy density of states of the system. So because of the fact that this is a gravitational theory, this is a somewhat richer theory than a standard low energy effective quantum field theory. And this is why this is also a bit more interesting than a basic low energy approximation to a conformal field theory. So the prototype computation that illustrates maybe some of it is, suppose we compute a partition function at finite temperature. And the exact partition function of the field theory is just this obvious answer here with some discrete spectrum of energy eigenstates. So these energies, EI, they are very difficult to compute, certainly at high energies, because it's a strongly coupled chaotic theory, and we don't really know how to do that. Nor do we have any clue how to do it on this side. What you can do is do a low energy approximation. If we do a low energy approximation and we compute the entropy of a large Schwarzschild black hole in ADS, then we get this answer. Just this basically follows some conformal invariance, so with some particular scaling of the temperature. So we have to do something to this exact answer to make it look like that. Now, it is well known that if you rewrite this in this language by expressing it in terms of some density of states rho of E, that we get some continuous density of states rho of E, which scales with some power of E. And for example, when D is 2, this is basically just the Cardi formula, the density of states. There's an E missing, a little E here. It goes like E to the square root of the energy. Now, what we normally say is that here we have all these discrete energy levels. This is this continuous energy spectral density, that you have to do some sort of coarse graining to go from one to the other. And that coarse graining is somehow essentially corresponding to doing this low energy approximation. So what's coarse graining? What does that word mean? It's a bit of a heuristic term, I think. I don't think we have a very precise definition. But morally speaking, coarse graining is something as follows. We take the exact answer, then we smear it against something, a kernel, and that kernel could, for example, be a narrow Gaussian or something like that. And what it does, it blurs the details of this exact energy density. And if you blur the details of this exact energy density, you may well end up with a continuous spectral density on the left-hand side. As long as so at very high energies, this rho of E will have a very densely spaced spectrum. And if you smear it against a Gaussian that contains sufficiently many of those lines, and you do that integral, you'll get something smooth. So that's heuristically what we mean by coarse graining. But it's not very precisely defined because we have some choice to make what K is and so on, and maybe the choice is not so important. But this is clearly in spirit what is going on here, but it's not very precise. You could also equally well write something that looks more like an average, but it's morally the same thing, where we take, rather than smearing it against the kernel like that, we take the original spectrum and we change it slightly. In such a way that it really is indistinguishable from a low energy point of view. So you could change these high energy levels, you could change them ever so slightly and wiggle them a little bit. You would not see the difference at low energies anyway, and then you could average over all these slightly dispaced spectra, and then in that way you could also go from an exact spectral density to a semi-classical spectral density. Again, here, it's not exactly clear what we mean and how to do this, so these are sort of morally speaking correct, but technically a bit imprecise. Yeah.
The first one is more like a microcanonical binning, right? So,
yeah.
And the second one is to just replace the rho exact by something, anything, which agrees.
You just do tiny displacements in such a way that if you, again, would do this smearing, it would not have any impact.
I see.
Yeah, so in that sense, it's very similar. Both are very similar.
Okay, thank you.
Yeah, as I said, this is, you choose this mu in some way. Clearly, you want the integral of d alpha mu alpha to be 1, so that the total integral of the thing remains the same. And for the rest, it's a vague statement, I admit. So the whole point is to try to come up with something that's a bit more well-defined than what's written here. So at this moment, you could, any mu that has support, I have also not defined for you what rho alpha is, so it's only the combination that makes sense. And again, the idea was to take the spectrum, you displace it ever so slightly, and you average over those, whatever that means. Yes.
On this side, those alpha spectra are
yes.
somehow the average.
That's right, yeah. Now the simplest, if you have one energy, one line like this, and you average over all of these over some interval, then the result of the average is some continuous density that's like so. With the property that this is, if you have one line, then you just get something that has, you know, if you integrate it, it's 1, because the area should be preserved. With the rest, you could do something like this. So. Yeah, and this is a very, this in some sense is a very generic observation that could happen, right? Yes. So in order to do something slightly more precise, if you want to write precise versions of these equations, what we can do is use the principles of statistical physics to do so. And that gives you in some sense, a preferred method to do this. And that goes back, in some sense, all the way back to Wigner in 1955, when he wrote down a model for the energy spectra of heavy nuclei. But the idea is roughly as follows. So I'm going to take this second point of view, and rather than, I'm going to replace this displaced exact spectral density by a slightly different Hamiltonian. You can exchange a Hamiltonian for the spectral density. These are just the eigenvalues of that Hamiltonian. So rather than writing something like this on the space of spectral densities, I'm going to write something like this on the space of Hamiltonians. And the idea is that there is something that we don't know, which is the exact Hamiltonian. And then we're going to displace that exact Hamiltonian slightly, and we're going to average over all those Hamiltonians to technically accomplish what's written here. So now the principles of statistical physics translated into this context suggest the following. To find the right measure on the space of Hamiltonians, so this mu of alpha here, it's now replaced by a mu on the space of Hamiltonians. To find the right measure on the space of Hamiltonians, we're going to optimize the entropy. That's the classical entropy associated to a probability distribution. It's the Shannon information, if you wish. So it's the classical version of von Neumann entropy. And that is the way in physics in which we quantify the amount of entropy there is in a probability distribution, or equivalently, it quantifies the level of uncertainty or ignorance that we have. And the basic principle of statistical physics is that we should always maximize our ignorance subject to the information that's available, which then gives us the optimal description of the system in the sense of statistical physics. So what we do is we write this entropy minus mu h log mu h, and then we add to that the idea that we still want that if we compute the thermal partition function, it has to agree with the semi-classical answer that we computed. So the z of beta here is not the exact answer that we do not know, but it's this approximate answer that was standing here. And we want this to be true for all values of beta. That's our semi, yes?
Doesn't that fix the entire spectrum?
No, you see, what you do, it does not. Because if you, the z of beta had a continuous spectral density. And each h here has a discrete spectral density. And there does not exist a single choice of h, which gives you a continuous spectral density. So although this can be achieved, you can only do it with a suitable mu of h, which converts all these discrete spectra in something continuous. If z of beta was the exact answer, then the outcome would be, then mu of h would be a delta function that is localized on the exact Hamiltonian. Because z of beta was an approximate answer, mu of h will not be a delta function. It will be something that basically tells you then when you do suitable smearing, you precisely get the semi-classical answer.
So yeah, and this is also the same as the Jaynes S maximization procedure, right?
Yeah, that's correct. That's very correct. Yes, thanks. Sorry, was? Yes, yes, exactly. Yeah, yeah. Otherwise, clearly, it would not have a solution.
Question? Sorry, how is this a Jaynes entropy? How is this a Jaynes maximization? In Jaynes maximization, you keep a couple of operators, the expectation value of a couple of operators fixed, and then you calculate the von Neumann entropy of all the consistent density matrices.
Yeah.
Here, you're taking a probability distribution over H.
Yes.
And these
So,
H need not commute.
No, no, but you're right. It's slightly different because it talks about the density matrix and operators, but for the rest, morally it's the same thing. It's not technically exactly the same, but it's the same underlying principle. That's right. Now, if you go through this exercise, so you just maximize this quantity by just a little variational exercise. You just vary the measure mu of h, and then you compute mu of h. Then you will find that mu of h, it's trivial, will have to be of this form. That's the result of the optimization. And these Lagrange multipliers, this continuous family of Lagrange multipliers still stands here. And those you then have to fix by demanding that this theory produces precisely those expectation values, as always. Regardless of the detailed choice of lambda of beta, what the statement is that this is going to give you a matrix model for the Hamiltonian, a single trace matrix model with an unknown potential V of h. These lambda betas can be anything, so this can pretty much be anything. It is some single trace function of h. And this single trace function of h you have to fix so that it precisely reproduces the answer. And there are well-known methods in matrix theory that tell you that if you want to get a particular spectral density, how you fix V. There's some simple integral equation that relates V to the spectral density in the large n limit, and that is the sort of equation that you can use here to determine V of h. I don't think it's very easy to write a simple explicit h for this particular rho V, but it's implicitly defined by some integral equation that you could try to work out if that was useful. So in this way, we get a preferred choice for this measure mu here, which is given by something like this, a single trace matrix model. And the idea here is to show that this shows that if you have no other information about the system, we typically do, but if you don't, if you have no other information about the system, then the best description of the Hamiltonian of a theory with a continuous spectrum is in terms of such a single phase matrix model. That's the best possible description in the sense of statistical physics. And now if you have a chaotic theory, it might be very hard to get more information about the theory. For example, how can we get more information about the high energy spectrum of the theory? It's very difficult. Might not be impossible, but it's very difficult. So if you have a chaotic theory, it might actually be hard to do better than this. So if you have an actual chaotic theory, perhaps this is the best that you can do, and that would suggest that the best possible description of the chaotic part of the spectrum is in terms of some matrix theory. And that resonates nicely with the so-called BGS conjecture, which states that if you take a classical system, which is classically chaotic, and you quantize it, that the energy levels of the quantum theory are effectively described by random matrix theory. The claim here is not that we solved something exactly. We did not. We did not solve n equals 4 super Yang-Mills theory strong coupling. We just said that if all the information that we have about that theory is based on the semi-classical approximation, the best model, as a physicist, the best model that we can make for the spectrum of the theory is in terms of a random matrix theory. You can repeat this game for other objects. So more generally, if say you have a set of correlation functions or some other data available, these observations fi of a, so these are some correlation functions, and you want to make a measure on the space of operators, which for example could be the set of matrix elements of the operator or something else. You can do exactly the same thing. You can write down this Shannon entropy, you can write down Lagrange multipliers that constrain all the input observations as constraints on the theory. And what you get out is, again, some probability distribution on the space of objects A with some coefficients lambda I that you have to fix in order that these expectation values come out to be correct.
Like bit different Dyson index and stuff. Like, so is there any semi-classical way that understanding this index from the potential, the previous slide that you have shown? Yeah, this one.
The index on the potential?
Like Dyson, like which kind of random matrix theory will be like an orthogonal ensemble or unitary ensemble, or is there any semi-classical?
Yeah, that again is a question about whether you have extra information available. So if you have no information about the theory, you just know it's some quantum system, and all that you know is that it's a Hermitian Hamiltonian, so you get to the usual Hermitian matrix model. If you happen to know that your theory, so that's extra information that you have available, that your theory has additional symmetries, then you could constrain H to lie in a subspace of all Hamiltonians that's consistent with the symmetries of the problem. Then you would still do exactly the same exercise, but you would get a modified matrix model where you only integrate over those Hamiltonians that have the required symmetries. So it's always true there that what you get at the end depends on what the information you have available at the beginning. And if you have these additional symmetries available, you should put it into your model.
Okay, thank you.
And the simplest possible example is that if you only have quadratic observations, things that are quadratic in A, then what you get is something that looks Gaussian. You get e to the minus something quadratic in A. So another example where you can apply this logic, which gives rise to a familiar result, is suppose that we have some semi-classical computation or some low energy or some approximate computation of the finite temperature 2-point function of an operator A as a function of beta and t. So if we put complete sets of states in this correlator and we expand the correlator, I put e to the minus beta over 2h in two different places, but that's not so important. You expand it in the matrix element, you get this expression here. Now, if you know this quantity as a function of t and beta, you can sort of undo, and you also know the spectral density of the theory. You can undo the prefactor and you can derive what these matrix elements are, given the fact that you know all these 2-point functions. And then But again, you find matrix elements that are inconsistent with a single microscopic operator A. By the same logic as before we got a continuous spectral density as opposed to a discrete spectral density. Now you can ask, can I make a statistical model for these matrix elements based on this information? And this information is semi-classical. For example, in an ADS-CFT context, this information is semi-classically available because we simply do a two-point function computation in the black hole background. We put two operators on the boundary and we just compute the propagator and so on and so on. Now, since this is quadratic information, the outcome of this is a quadratic matrix model. And the outcome of this, the result of this exercise is that you get the eigenstate thermalization hypothesis. You can ignore the first term for this purpose, but the eigenstate thermalization hypothesis is precisely a statement about matrix elements of simple operators in high energy eigenstates in quantum many-body systems. And the statement is that for all practical purposes, these matrix elements behave as if they, up to some coefficient here, they behave like a random matrix. It's a hypothesis and it's claimed that in a chaotic many-body system, this is a good way to think about these matrix elements. Yes?
So here in your previous slide, to get this, what you did was that you replaced the two-point function on the left with the expectation from the black hole physics, which is this just decaying. Is that what you did? And then you solve for these guys.
Yes.
And you're claiming you get ETH, like what aspects of ETH can you reproduce? Like the whole thing?
Yeah, you get literally this because as I'm sure you know very well, this GA here has the only information it contains is the information from the two-point function. So you can apply this to any two-point function. If you take the particular two-point function that you get in a black hole that has the famous exponential decay, you get a particular answer for G of A for this prefactor. But if you take another two-point function, you simply get a different answer for G, but the structure of ETH remains the same.
I guess, for example, E2 minus SE over 2, is there a natural way of seeing that?
Yeah, but that is simply follows from the fact that this thing has to reproduce the right two-point function that you started out with. And the E minus S, it's just convention to put this in front of G. And it simply has to do with the fact that if you go back to this thing, you have a sum over I and J. If you write it, say, as an integral with a spectral density, then you get E to the plus S's. And in order to get something finite and order 1 at the end, you put the E minus S over 2 here. That's the usual reason why it's the same reason here. Yep. Because you still want this thing to correctly give you the two-point function. Yeah, for this computation, I just used the continuous spectral density that you have semi-classically available, and I did not independently, I'll come back to that in some sense, but at this moment I did not. It was just a statement about these matrix elements. Yeah, and this is the usual way it's written. So here these RAs are unit normalized Gaussian random variables, but the whole thing is just still a Gaussian random variable. It's just not unit normalized. So this is one way to quote unquote derive ETAs from statistical physics principles. It does not prove it's valid. That's not the statement. The statement is simply that in the absence of other information, the best description of these matrix elements is in terms of ETH. If you have no other information about the system available. And as before, if you have a chaotic system, it might be very hard to get this additional information. And therefore, in a chaotic system, the ETH is a very good approximation to reality. That is what would follow. But it doesn't prove anything, just like ETH cannot be proven. This does not prove anything, but it explains why ETH is a very natural thing to write down if you have a chaotic system and you want to model the two-point function. It's pretty straightforward to include higher point functions in this game, and then you simply will get higher point correlators for these objects R. Like if you input a 4-point function, then you get a fourth order matrix theory and you get a fourth order correlator. So these things become non-Gaussian. That's also known. that you could incorporate if you wanted to, but it doesn't really buy you too much otherwise. Okay, now this was just a general framework, so now we want to apply this to ASCFT. Yeah, this statement was completely agnostic about the input. As long as you give me some input for this two-point function, ETH follows. I could specialize to the case of an actual semi-classical computation. Then I would get ETH, but also with a very specific choice for G. And that G would be precisely, you have to find, I don't know exactly what it looks like, but it will be the G that gives you the exponential decay of the two-point function. You would have to do a semi-classical, you just do a Witten diagram in a black hole, do the three-point function and four-point function, etc. Yeah. I did not. People have. GA is essentially, in an explicit example, is some sort of, it's related to some sort of inverse Fourier/Legendre transform of this two-point function. So there's an explicit expression for G in terms of the two-point function that you could work out if that was interesting. Yeah.
Distribution or particular measure for R is being singled out. I mean, it's random, but randomness comes with some particular distribution.
Yeah, in this case, it is this unit Gaussian random variable. That's the distribution. That distribution follows from the optimization of this particular quantity with this particular choice of entropy functional. Now, if you're very precise, you might want to argue that you might as well have chosen another information theoretic measure here. You might have gotten a slightly different result. But this clearly is the thing that we like in physics a lot and gives us statistical physics and so on. But in principle, you could put a more obscure version of information here, and you might get slightly different answers.
Sorry, another quick question. So you related the form of ETH, that form of ETH, with the expectation from the decay of the two-point function in the thermal background. Now, you made a comment about higher point functions. There is an extended ETH conjecture out there. What does that intuitively correspond to in terms of the coarse grain expectation? Like if I want to, yeah.
Yeah, if you repeat this exercise, and again, if you input 3 and 4 and higher point functions at finite temperature, you get a matrix theory-like object here that has higher point correlators. So this is no longer a squared, but a cubed. So if you compute, and then you could compute the moments of all these a's in this distribution, and that would be the generalized ETH. So literally R would no longer be Gaussian. It would be governed by a more complicated matrix theory, but it's not single trace in the naive. It has some functions in it, so these f's and g kind of appear in this potential here, but it is still, you just get non-Gaussianities for R, so it agrees with these proposed higher order versions of ETH.
Maybe we could discuss this offline. Thank you.
Yeah. That information is not available, but if I want to apply this formalism to a semi-classical gravitational theory, then what I'm going to use as my observables will only be correlation functions of simple operators, because those are the only ones that are semi-classically available. So then the choice of simple operators shows up in the available information that I put into this system. Yeah. Well, for the A's, so the A's would only correspond to the simple operators with low conformal dimensions, because I do not know how to write down a if I write a very high dimension operator, I don't know how to write those in a semi-classical theory, like say an operator that creates a particular black hole microstate. I don't know. So this information is not available, so I should not include it in any of these computations. Very good. You could do it for quantum field theory. This is completely agnostic about the system that you're in. ETH is valid, yeah, but it also applies in this sense if you just apply it to a CFT on a sphere and you do mutuals, it also applies, yeah. Good. So now we want to apply this to a semi-classical gravitational theory, and we want to explain precisely what is supposed to be in the bottom left corner of this diagram I showed before. So what we're going to do is we're going to collect all our semi-classical computations, and we're going to input all those semi-classical computations in a fancy statistical model. Clearly, it's very difficult to take all semi-classical computations into account, but let me just try to explain a bit what type of information you do in the case of, say, a 2D CFT, because that's the simplest example to maybe explain explicitly. So in a 2D CFT, typically what you have in a semi-classical theory, you only have some light fields in your supergravity theory. So those are the only fields available. We'll roughly denote the things that you have semi-classically available by L for the light fields, and the things that you do not have available by H, heavy fields. And then there's all kinds of quantities that you can compute and cannot compute, but you know, the details are not so important. Then, for example, one thing you can compute semi-classically is a 4-point function. You just put 4 light operators on your sphere on the boundary, and you just do the Witten diagram computation. From a CFT point of view, the corresponding computation is a 4-point functionation in the CFT. And we're especially interested in the case where this thing here, in the kinematic regime, where this is dominated by high energy operators. So you have to put the 4 points in a particular alignment to make sure that this happens. But you can figure out what it is by using the right cross ratios. And then this computation from a CFT point of view will involve lots of kinematic factors and conformal blocks and what have you not, but it also will contain a sum of squares of OPE coefficients. You have an OPE, operator product expansion coefficient here and one here, so you get a square of OPE coefficients times, in principle, known kinematical factors. You can do the same for a 2-point function on a torus in a 2D CFT, and again, it's going to be something quadratic in OPE coefficients, and you can do a genus 2 computation, of which this is a cartoon representation. And if you compute a partition function of a genus 2 Riemann surface in a 2D CFT, you get again something quadratic in OPE coefficients. So suppose that the only semi-classical computations you were going to do were these computations and not something more complicated. Then what you would get is, just like in ETH, you would get equations that tell you that this times something else is equal to something that can be semi-classically computed. These are all quadratic expressions in OPE coefficients. So by just taking all the same steps again, what you get is some quadratic matrix model type thing for the OPE coefficients. It's at this level of the discussion, if this is what you put in, and you do the steps that I outlined, you get a quadratic theory for OPE coefficients. They look like random Gaussian variables, essentially. So the combination of, and if you also include the computation of the entropy of a black hole, that gave us the single trace matrix model. So if these are the sets of computations you put in, then at that level you get a combination of this matrix model that gives you the spectrum plus a quadratic model for the OPE coefficients. That is because my computations that I chose, I can do better, but if I only do these computations and I restrict my semi-classical computations to this set of computations, and from a CFT point of view, all these computations only involve things that are quadratic indices.
That's because, I mean, you're saying you want to compute only the second one. So naturally,
I chose to do that only. Yeah, I could do more, but at this level, let me just for simplicity, you can do more complicated computations and then you get something more complicated. Just like in ETH, we only have this random, this thing R. And if you only look at 2-point functions, it's Gaussian, but if you want to do higher moments, it will become non-Gaussian. The same is true for the OPE coefficients. All right. So this gives rise to something that we call the OPE randomness hypothesis. It is just basically a version of ETH that now applies to coefficients of the operator product expansion. And now if you do something a bit more complicated, then you also know that in principle you get higher moments for the OPE coefficients, but also in all these computations, you have a combination of the OPE coefficients and the spectrum of the theory. So if you do it more precisely, you also get correlations between the spectrum of the theory and the OPE coefficients. So the full answer that you're supposed to get at the end is not just these two pieces, but then interacting pieces. Things that let the C's talk to themselves at higher order, things that correlate OPE coefficients with M, etc. So we get some sort of complicated matrix tensor model if we input all this information that describes the theory. So this is how you come up with the semi-classical theory. Yeah, so I have determined V by computing C of beta, and I've determined this V by computing the all these 2-point functions, like the 4-point function on the sphere, the 2-point function on the torus, and the genus 2 Riemann surface computation. That gives me this left-hand side, from which I determine that V. This I do from a black hole partition function computation, that gives me that V, but then all higher order things will correlate all this information. Yeah, given a particular Z, you will find a particular V. And vice.
So if I give you a random Z, like from semi-computation, it is possible that you can find a particular M.
Yeah. You just have to do some, you have to invert some equation, but yes.
Okay.
Yeah. Yeah, the H, they will be above the black hole threshold. That is the sort of regime where, yeah, you don't have microscopic information available. That's right. Yeah.
Is it analytic? Because you also have the formula of CHHL.
Yeah.
Are these analytically related or they are totally different formulas?
That's a very good question. It's also a very difficult question that I don't know if I can answer in generality, but if you take sort of in pure 3D gravity, the answer seems to be yes, because in some sense conical defects very often, conical defects are describing the thing below the black hole threshold and black holes above, and very often these equations are kind of analytic as you cross from the black hole to conical defects. To what extent you can make a similar argument in a more general CFT, I'm not entirely sure. This region around CO12 is very hard to study analytically, so you know, even just the spectral density there in the general theory is very murky. So, all right, I'm doing very poorly time-wise, but let me just explain why this is good for anything, because it's amusing to build this model, but is it good for anything? And just to make sure I get the punchline across, I think there are several reasons why this is a useful perspective. One useful perspective that this gives us is that it explains the factorization problem. And it also, I think, sheds light on how it's possible that using only semi-classical gravitational computations in the theory, you can still see part of information recovery, which a priori might be very surprising. You might have thought that to get the page curve for black hole creation and evaporation, you need a full UV complete microscopic theory. But as was shown a couple of years ago, with suitable semi-classical computations, you can actually get the page curve to come out. You might ask, how is it possible that the semi-classical approximation can get this page curve to come out correctly? So let me just make those 2 points and then omit all the rest, basically. So the factorization problem, as you probably have heard before, is the apparent puzzle that if you have, say, a Euclidean wormhole with a cartoon of this form, it has 2 boundaries. And the fact that these things appear in the semi-classical gravitational path integral seems to suggest that if you put, say, 2 finite temperature boundaries here, that the connected correlation function of 2 partition functions is not the product. Because the product would just be a geometry that caps off times a geometry that caps off. And this is an additional piece, and this seems to give rise to this weird statement here. Now this statement is not true in an exact CFT, because if you put a CFT on 2 disconnected manifolds, it is just the product of the 2 theories. So from this statement and the fact that these things appear in the gravitational path integral, you can see that in the semi-classical approximation, this is no longer true. And that seems to be problematic. Now you could say, well, that's very bad. That means that we have misunderstood ADS-CFT, that ADS-CFT should be replaced by a statement that an average over CFTs is equal to the gravitational part of the answer. But I'd like to emphasize, we did this computation only in the semi-classical approximation. Now what's important is that if the semi-classical approximation, as I tried to explain, is dual to a statistical theory, not to a single theory, but is best thought of in terms of statistical physics language, then that statistical model does predict that you will have such correlations. And those correlations are not fundamentally there, but they're an artifact of our ignorance that we have as semi-classical observers. As a semi-classical observer, we cannot see the full UV of the theory. We only see this low energy effective field theory. We are ignorant. And as a result of that ignorance, our best possible description is in terms of a statistical physics model. That statistical physics model clearly violates factorization. Because if I, for example, compute this product of two partition functions and I do my statistical average, it's not equal to the product. Now, you could say, well, that is just, okay, then wormholes.
I have a quick question.
Yeah.
So you had a statistical model for each of Z of beta, right?
I made a statistical model for one Z of beta, yeah, for one theory.
Right.
I did not attempt to make a statistical model for two theories.
Yeah, so what tells me that this is what I should do? I mean, I should take the average after I compute.
Good. You might also have said that this is wrong. It's basically follows from the computation that this is the way to think about the theory. So somehow the semi-classical theory is an average. And if you have a connected geometry, in some sense, each connected geometry represents a single statistical thing, not two independent ones. Because it would be funny if a connected geometry was two independent statistical things. It seems to be at odds with the topology of the manifold. So the right way to think about connected geometries, if you want, it's an additional ingredient in my proposal, is that whenever you have a connected geometry that connects multiple boundaries, this is to be thought of as a single average, a single ensemble, and not as something more general than that. And you can test this idea, because if this is true, then what you do is you do all your computations with just a single boundary. In that way, you build a statistical description of your semi-classical gravitational physics. Then you can use that statistical description to try to make a prediction for what a wormhole would give you. So now the wormhole is not an independent computation. You can just take my statistical description, I compute this mu of h in a single boundary theory, I stick it into that equation, and I get a prediction for this correlator. And you can compare that prediction with what you would get from a gravitational wormhole. And the conjecture is that these things always agree, so that wormholes do not contain any interesting new information. They're just telling you that gravity knew all along that it should be described in the language of statistical physics. And you can test this in several examples, and this conjecture seems to hold. It's hard to prove or anything, but this seems to be a true conjecture. And the rough intuition for the conjecture could be that if you build your, if you input all this one-sided information in this statistical model, so that statistical model has the same information as the gravitational theory, what it knows, it essentially knows about the entire Lagrangian of the bulk theory. You can reconstruct all the coupling constants order by order and so on. And if you know what the Lagrangian of the bulk theory is, you also have all information available to compute what the wormhole is supposed to be. It's very heuristic, but that might be the reason why this conjecture might be true, and why wormholes really fundamentally contain no new information. Yes, Johanna? Yeah, because it's maybe related to the previous question. So if you have to do a single coarse graining simultaneously on both sides and not independently. If you did an independent coarse graining on both sides, you would indeed, as you say, destroy correlations. No, but the starting point here, this is the... Yeah, but the starting point here was the statistical model, which has correlations in it. And those are the correlations we're talking about. Oh. We have a few more minutes because there were many questions. Yeah. So that's the conjecture. And you can test it, especially in ADS3, quite well. Especially in a pure 3D gravity theory, you can more or less prove that this conjecture holds using some techniques from topological quantum field theory. So the simplest possible, just to give you the flavor, for example, this simple on-shell wormhole that you have in the semi-classical theory is the Maldacena-Maas wormhole, where you have basically the boundaries are genus to Riemann surfaces, and you just have a throat that connects them. As I told you, with genus 2, partition function is something quadratic in the C's. We had a quadratic matrix model type thing for the C's, or tensor model if you wish. So clearly, if you do this correlator, there's also another Wick contraction in the Gaussian theory, and you can check that this other Wick contraction is actually computing the wormhole. So this is how, once you promote these objects to statistical objects, you get correlators between these quantities and how you reproduce these wormhole computations. You can also look at the spectrum of the theory. There's also a correlator here. You can ask how can this universal, this is by the way a universal result in single trace matrix theory that does not depend on the potential V, so that's kind of amusing. How can this universal matrix model result be recovered from a gravitational computation? Well, for that you have to cheat a little bit. You have to go slightly off-shell, and I'm happy to talk about it later. But if you allow yourself to go slightly off-shell and use something like constrained instanton approximation, then you can also get this universal matrix model correction from a gravitational computation. So that's again suggests that with a little tweak of what we mean by semi-classical gravity, we can also get this particular correlator as further evidence to my statement. And the last little point I want to make, and then I'll wrap up, is to explain, if you believe this picture, why, although you have all this averaging and coarse graining going on, why you can still get see the page curve to come out if you look at an evaporating black hole and so on. So in this statistical description, if you start with an initial state rho 0 and you time evolve it, at a given moment in time, it will be given by some classical statistical average of the time evolved density matrix. There should be a 0 here. Sorry. It will be given by this classical statistical average of a time evolved density matrix. So this is a classical statistical mixture of states. Now, if you just take that thing here and you just do this integral, you get some mixed state, and typically its entropy will increase as a function of time. And that's the usual, you say, if you wish, Hawking's computation. But if you are a bit more precise and you compute not the entropy of the average state, but the average entropy of the state, then, well, that's most easily done by just looking at the Rennies. So if you compute raise rho t to the n and then average, if you first take the nth power and you then average, then it's easy to see that if you take this to the nth power, you just get e to the minus iht rho to the n e to the iht. And if you then take the trace, you know, by cyclicity of the trace, this all collapses, so you just get trace rho null to the n. And because this is true, it also means that this entropy after averaging is actually equal to the initial entropy. So you see that although by doing this kind of procedure, we are removing a lot of information about the initial state, the fact that in this gravitational description, it is effectively a classical statistical mixture of states. You should not think of that classical mixture of states as a single state. It remains a classical statistical mixture of states. That's the reason why the entropy after averaging remains fixed. Now, this is a very cartoonish representation, but this is the reason why in a semi-classical theory that has all these integrals and all this statistical stuff in it, you can still have energy of information conservation. And the key is this classical statistical mixture of states, which is the real description of time evolution in this theory. And to see this phenomenon, you clearly have to do replica computations, and it's precisely the replica wormholes that make this happen. And you can make a toy model where you, a very simple toy model with some random unitary dynamics where you can really see that what I said is true, and that essentially a version of wormholes are the things that are needed to make this work. So replica wormholes also, they are a bit different from the Euclidean wormholes I described before, but replica wormholes are also part of this discussion, and they are again needed to see their their impact on the computation is again completely consistent with the statistical interpretation that I gave. So these replica wormholes are the key to do these types of computations, and replica wormholes are the thing by which you can distinguish a classical mixture of states from the average state. That is what you can distinguish with a replica computation. And this, I think, explains why a hybrid combination of a classical and a quantum computation was able to get the page curve to come out. And this is illustrating how it works on the classical side. I have several other slides and I have no time. I just wanted to mention that it's a very interesting question in general, how you could possibly restore factorization as you go up in my original diagram. So below I had a statement that the semi-classical approximation is equal to some statistical description. As you go towards the UV, you hope to recover the exact ADS-CFT duality. So somewhere along going up, you need to see that factorization gets restored. And it's an interesting question whether there is a general mechanism that does it and what that general mechanism is. Perhaps that mechanism cannot even be formulated in the language of semi-classical gravity. Maybe it is just proper quantum whatever. But it's still interesting to see how that would work. So maybe almost any possibility here has issues. So I don't know what the general answer is, but I think it's an interesting open question. And another interesting open question is to understand better all these off-shell configurations that you seem to need. Tiny off-shell, not too tall, that you need to make this work. Those are two open questions, and I had some other things to say, but I'll stop here. Thank you.
Some urgent question, Bartek.
I don't have anything particularly useful to say because it sounds very similar, because here we are erasing some information and we are replacing that. But to what extent it's entanglement with hidden information as opposed to the statistical description, that is the right, I don't know if there's a map from one to the other, so that I don't know.
Alok?
Yes, they will approximately satisfy crossing and everything. So, but that's because the gravitational computation satisfies approximate crossing. So it follows from the gravitational computation. One thing I did not have time to say is that you can also do something very different. Rather than doing the statistical approach, there's two other ways you can try to do it. And another way to do the statistical approach is to not write a matrix tensor model the way that I did, but to write a very different type of theory, where you basically take all the axioms of CFT. So you basically exponentiate all the bootstrap equations, and you write something like this. So this looks a bit like this Brownian motion theory that Jonathan wrote down yesterday, like where you exponentiate all your field equations. It turns out that this model, which is much simpler, because this truncates at fourth order, because one of the equations here is crossing times crossing, which is fourth order in OP coefficients. This is just a fourth order theory. This seems to also give you all the right correlation functions, except it's very different in spirit. I think the two theories, the one that I described before and this matrix tensor model, are somehow equivalent. And one is simply the generating function of correlation functions of this one, but this might be the simpler description. I just don't know whether this generalizes, but yeah, that's yeah.
So let's postpone the rest of the questions to the coffee break. We are hopefully out of time, so maybe we start at 11:20. Yeah. Okay. Thank you.